Okay, today, welcome to Chemistry with Miss Bouquet. And what we're looking at today is comparing boiling water with the decomposition of water using electricity. So on the side here I've got a Hofmann's voltameter set up, and the purpose of this is by using electricity from our transformer, our power pack. We've got the red lead to positive, the black lead to negative. And I'll just move this across. You can see we're going to be putting electricity into this, and with a bit of acid in there to make it work a little bit faster, we'll be seeing the two gases that are formed when water splits. So you can already observe that there are gases produced, that there's fizzing and bubbling occurring when I turn it on. And after a little while we'll notice that the levels of gas will form in this area here. Okay, while that's happening, I'm going to do a very simple experiment of boiling water. And in this experiment, what we're going to do is compare how we know that this is a physical change and that we can't decompose water by boiling it, but by putting electricity through, we actually can. And the idea here is looking at the bonding going on and comparing how the different amount of energy that we give it changes it chemically, or if we have less energy, it only changes it physically. So, I always like the match first because it doesn't always enjoy lighting. Okay, new one. Bunsen is on, and turn to blue flame for heating. Okay, so we've got water in here, water in there, and we're going to see the difference in how they change as we add the energy to it. Welcome back. Now, after about 5-10 minutes, you can see that our water is truly boiling. You can see all the bubbling, and there's definitely a gas being produced. There's a lot of it, and you think, wow, that's a lot of energy being given there. But over here, in our Hofmann's voltameter, you can actually see something extra. Definitely there's a lot of gas being made, but in particular you'll notice there's twice of one gas being made to the other. So we're going to actually do some tests to see what gas could be made here. Firstly, when we look at water, a water molecule is formed from one oxygen and two carbon dioxide, one oxygen and two hydrogen molecules. So really the only gases we can get out of this is water, oxygen or hydrogen. Unfortunately there's tests for those. So the first test that we can run is a pop test. You get a lit splint, you stick it in the gas, and if it pops we know there's hydrogen there. Let's try it here. Well, it went out. Carbon dioxide also tests positive by extinguishing a flame, and so does water, because the water takes away the heat of the flame. So I'm pretty sure it's not hydrogen. For oxygen, it's slightly different test. Similar, but a little bit different. Instead of having a lit splint, we have one where there's a glowing ember. When you stick it in to oxygen gas, it will start to glow brighter or even reignite. So if I stick this over, again it's going out in the light. So I've exhausted my options. It can't be oxygen gas, and it's not hydrogen gas either. So I'm left with only one more gas that it could be. So by default it should be water. So all that we're seeing here is water changing from a liquid state into a gaseous state. And that means that all these water molecules are being jumbled around, more energy is given off, and instead of being closely linked together in a liquid, they're much further apart. They're spreading out and filling up the room, making it more humid than normal. But they're not changing their bonds. These two covalent bonds between the hydrogen and the oxygen are not being changed. And that's the key part to a physical change. You're changing the physical state that a chemical is in, but you're not changing its chemical properties. This is water no matter what. If I stuck a lit splint into the water, it would not reignite. Okay, it would do the same thing the gas did. However, if I had liquid hydrogen or liquid oxygen, they would also test the same as the gases do. They're very hard to make. Over here, we have a fair amount of gas, so I should be able to do a gas test. I'm just going to turn off our water. There we go. Alright, so we have enough gas, and I'm going to turn this off for the moment and show you what happens with the two tests here. To start off with, I think it's important to recognise the chemical formula of oxygen. Oxygen is H2O. There's 2 hydrogen atoms and 1 oxygen atom. And it's important to realise this because when they form their elemental molecules, you'll notice that hydrogen forms a diatomic, a 2-atom molecule, and so does oxygen. It's got a nice double bond there, a 2-atom molecule, so both diatomic. But because there's 2 hydrogen and 1 oxygen, and to make oxygen gas you need 2, to make a balanced equation we actually need to start off with 2 waters and break that down into 1 oxygen molecule and 2 hydrogen. The significance of this is when we look at the Hoffman voltameter, you can see we've made twice as much of one gas than the other. If we are going to use a bit of logic and reasoning, even though they're smaller, you'd probably think, well, twice as much hydrogen gas or twice as many hydrogen atoms are in a molecule of water, so we should expect to see twice as much hydrogen gas compared to oxygen. Let's test out our theory. Again, I'm going to light the splint, and let's start off with doing the pop test. The pop test is basically hydrogen combusts when presented with a flame. It will react with the oxygen in the air. And because it's in a small test tube, it goes pop, nice squeaky sound. If it was in a big balloon, it would go bang. And it went out. Just try this again. Okay. We've got the gas in there, in our test tube here. Didn't even have to go far. Alright, I have a lit splint now, so it's really handy then to just do the next test, which is oxygen. There's our oxygen in here. And if I put it in, the magic starts, and I just reignited the splint. It's out now, got snuffed, but I reignited the embers that are glowing here. So that's indicative. We've got 2 positive tests. We positively tested that the gas on this side is hydrogen and the gas on the other side is oxygen. So the positive end produces oxygen, the negative electrode collects the hydrogen gas. And that we can see is a very different reaction than what we saw here, which was not a reaction, it's only a physical change. We're seeing different chemical properties of the gases made. In the case of electrolysis, because bonds are formed from electrons, we're giving the molecule enough energy to break these covalent bonds and not merely just break the intermolecular bonds between the molecules themselves. We're breaking the bonds within the molecule, breaking them apart and forming new substances. That's the difference, what we see here. It shows us that heat doesn't always break compounds down. Light's more energy and that breaks some compounds down, but a lot of our chemical compounds require electricity to break them apart from their chemical structure. So, the reaction of water being decomposed by electricity. Looking at the balanced equation, we start off with our molecule of water. Now we know 1 molecule of water will produce 1 molecule of oxygen and 1 molecule of hydrogen. But the thing is, we need to always draw oxygen as diatomic, O2, because that's its natural form. Same with hydrogen, its natural form is H2. So it's fine for hydrogen, but not for oxygen. We actually don't have enough oxygen on our reactant side. We've got 2 oxygen here, but only 1 oxygen here, which means that we need to multiply one of these units. We start off by actually going to the water and go, well, okay, let's look at having 2 water molecules. Will this balance it out? Now, those 2 molecules will form this 1 molecule of oxygen. And now we just have 4 hydrogens from the water. So again, we just make 2 molecules of hydrogen. And this is what we saw in our reaction. When we decomposed water, we had our water being split into oxygen and hydrogen gas, and there was twice as much hydrogen gas as there was oxygen gas. And that's showing that this is the balanced equation of what's happening here. We're going to go through balancing equations for all the decomposition reactions that we've seen now.